I'm here to talk about latency SLOs. How many people do something around SLIs, SLOs, error budgets, things like that? So hopefully by the end of this talk, you'll be slightly panicked about how you calculate them, perhaps how you use them, and perhaps why you use them. I don't think that they're a bad thing, but I think that some healthy skepticism is really important. I've been doing stuff in the industry for about 20 years. One of the things that I did for about 15 years of that was help large online entities handle explosive growth on the internet. So I ended up working with about 15% of the Alexa Top 100. That includes Google and Facebook and Apple, and then a whole bunch of other companies you've never heard of, or if you're old and used the internet back then and remember them going out of business. A lot of stuff in the adult industry and like Friendster and Ning and some other things like that. So some big sites and performance and economics of delivering performance were really important. So I spent a lot of time doing operations, but from a software perspective. So I've been hurt by every technology. So we're kind of here to talk about service level objectives. I think there's a lot of confusion on what a service level indicator versus a service level objective are. I'm going to conflate the two terms because from a mathematics perspective, you kind of need to take both of them together. But from a latency SLI perspective, the proportion of valid requests served faster than a threshold. So the question is, which requests are valid? I would argue that this is like 200 errors, 200 2XX codes and 3XX codes in your website. It depends on whether or not you're servicing web. We do a lot of distributed database work, so there are no 2XX codes. It's all like queries. So queries that have no error messages back to the users, the one that return 0 or more tuples successfully. We measure the latency of those and establish our objectives around that. So generally speaking, they're kind of two things that are go-to for measuring as an SRE to measure reliability. And the first and most obvious one is errors, like just measuring errors. And I'm not going to talk about that because I actually don't think that's very difficult. I think most people do that right. The other one is latency. And there is a third one that's emerging that's very, very valuable, which is saturation. So measuring saturation, which you can apply a lot of these concepts to, but I'm just going to focus on latency. So an example of a latency SLO is 99% of the homepage requests in the last 28 days served in 100 milliseconds. By the end of this, you will realize this is just a horrible SLO. But let's dive into what this actually means. So I'm sure people have seen graphs that look like this. This is actually a snapshot out of the Google workshop from 2018. So this is a graph that just shows you the latency in milliseconds on the y-axis. It shows you time on the x-axis, and it's showing you a running 50th percentile, 90th, 95th, and 99th. So does anybody have a graph that looks like this in their org that they kind of look at? Okay. So almost always this graph is actually just a lie. Like the numbers are not actually accurate. And we can kind of get into why that is because it's important. So each pixel there is some point in time, right? But it's actually not a point in time, it's a time window. So if I look at the first pixel, that one might be 12 minutes. Or 15 minutes. Let's say it's 15 minutes, that first pixel, that says that our 99th percentile was, I don't know, probably right around 900 milliseconds. So the problem is how did I calculate that the 99th percentile over that exact 15-minute period was that number? And the answer is almost always the tools you're using, the answer is wrong. They're not calculating it that way. You end up calculating the 99th percentile over each minute, and then your tool, when you zoom out, averages them together. So does anybody know what the average of a couple of 99th percentiles are? Rubbish, that's a good answer. I would say absolutely nothing useful at all. It's not a 99th percentile of anything. In fact, the only thing that you're sort of guaranteed is is that you know it's probably wrong. So the real challenge is how we measure the things that we're measuring and how we come to the mathematics of performing a quantile. So it's not P90s, it's not the average, it's kind of just a mess. So if you actually measured that same thing correctly, this is in a slightly different graph, but if you measure that and you actually calculate this stuff correctly, this is actually looking at every individual latency that's been recorded. So this could be, 100,000 a second over, a period of time. This is a different graph. We're only looking at 6 hours here. But each one of these lines in the line graph is actually the 90th percentile over every exact sample in that exact window when it was delivered. So a lot of times when you look at a P99 graph and you actually recalculate it correctly, your P99 is crazy higher than you thought it was, which means that you're blowing your SLO budget. And it turns out it didn't actually matter, and we'll get to why that is at the end. But the other times, it's actually much significantly better than you thought it was, and you've been wasting organizational resources striving to deliver better even when you were already delivering well. So there's a real risk in calculating this stuff wrong because organizations put people behind these things, right? You're investing money, you're investing focus, you're investing your team, you're investing people in trying to achieve objectives, and if you're not measuring it right, you're either not spending when you should or you're spending when you shouldn't. So there are 3 ways to really calculate SLOs. So the first one is to just store all of the logs. Now, I don't know if anybody actually does this. In low volume environments, it's not such a big deal. If you're doing a couple hundred requests a second and you want to store them for a year or 2 years, it ends up being not that much data. So you can actually just store everything you ever do, and then you can go back and do math on it. You can hand it to, pipe it through R, pipe it through GNU plot, and do whatever you want to do. I'm not a huge fan of this because I don't tend to work with companies that do 100 things a second. They tend to do 500,000 things a second. And the idea of storing all of that data with all its sort of needed dimensionality to answer those questions ends up being really burdensome. But the other reason that it's kind of like a tragic mistake to do that is because it's really, really slow. So if I want to answer different types of questions about it, it ends up being bad. So the other one, which is really sort of so anybody here use Prometheus to do stuff? Does anybody use histograms in Prometheus? Yeah, so the histograms in Prometheus aren't really histograms. They're sort of, it's kind of like the redheaded stepchild of histograms. Nice try is the answer to that. What they actually really are doing is counting the number of things below a certain threshold, right? And the real problem and the reason why they're not really robust histograms is because you kind of have to choose those thresholds when you set up the system. Everyone chooses them wrong. And when you choose different ones, you can no longer combine that data and do statistical analysis on it. So it's really kind of just a hodgepodge mess. But if you do choose the bin boundary correctly, in this case 100 milliseconds, you have a precisely accurate answer. You know exactly how many requests served faster than 100 milliseconds and how many total requests you had, so you know the percentage, and you can calculate that at any given time. So if you had just 2 bins in a histogram in Prometheus, 100 milliseconds and infinity, you now have everything you need to do to calculate an SLO correctly. We'll get into why that is wholly insufficient and disappointing in a bit. And the last way to do this is histograms. Technically, you can use other statistical methods like t-digest and moment sketches. I'll get into very briefly why I think that's not a good idea at the very end. So this is pretty standard. Does anybody do SLO calculations out of like Splunk or Elk or Elastic or anything like that? Yeah, couple people. Upside is I think you can pretty legitimately get the right answer. The other upside of that is that when you decide that you asked the wrong question, you can then go ask the right question and still get the answer, which is really nice. But it tends to be tough to do in real time, just because the way that data is stored and the way that it's you don't end up materializing the type of data that you want to materialize to answer those questions fast. So a classic example, something Splunkish would be like, I want to pipe all my data through stats perc90 as response 90 and perc99 as response 99, grouped by application name. So now I can actually see like the 90th percentile and the 99th percentile. So the problem is that this is missing some pretty critical information. Are you calculating the 90th percentile over like all of time? Because that's pretty weird too. Like, why would I want to do that? I actually want to calculate the 99th percentile or the 90th percentile over a very specific period of time. So counting the number of bad requests, which I dove into very briefly, this is sort of how Prometheus works, is that you count all the requests, then you count, in this example, it's 30 milliseconds. I count the ones above 30, and now I have these two numbers. I divide them. I have my percentage. It's beautiful. And because this is a continuous function, I can use the mean value theorem in calculus to say I can choose any point, 2 points in time. So I could choose 2 and 4 and take the difference between one and the difference between the other, and I know exactly how many requests in my SLO during that time period, and it's accurate during that time period. So if I have a start time and an end time, I can actually answer that question. Sort of the problem we'll get to is I was asking the wrong question the whole time. And this doesn't give me an opportunity to go re-ask a new question. Like, turns out 30 milliseconds is wrong, and I need 90 milliseconds. And guess what my answer is? I don't know is the answer. I have no idea what the answer would be if I changed that threshold. This is a pretty simple process. Like I said, you just count the number of good requests over the number of total requests, and you get your percentage, and beautiful. So the problem here, kind of the fundamental problem, is that you have to choose your SLO latency up front. So histogram data. Histogram data is the best thing ever. So the beauty of histogram data is that what you're doing is you're introducing like variability in value domain, right? So if I have a number of like 115 milliseconds that it took to serve, I don't actually need to accurately say it was 150 milliseconds. I can put it in a bin, maybe from 110 to 120. And as long as when I ask my questions like what's faster than 110 or 120 or 1,000 or 1,200, as long as I have the same amount of precision in my questions as I had in my bins, I can still get incredibly accurate answers to the types of questions we ask as SREs. So there are a couple of libraries that do this. The HDR histogram stuff is pretty interesting from Gene Till. The circllhist is the one that we wrote at Circonus. Both of those are open source, as is the tdigest. So I'm not going to dive in too much to why tdigest is the wrong tool for this job. But I'll have a slide about it at the end later, and I'll talk a little bit. Does anybody use tdigest or moment sketches or anything like that to do the calculations? Yeah, so it's a hell of a lot better than just using Prometheus and having the bins wrong. But it gives you, it's really interesting. Does anybody know when you calculate a quantile, how to calculate a quantile? Like, in general, what you do is you take all of your numbers. So I have 1 million latencies, and I want to figure out the 95th percentile. I sort them all, and I go 95% of the way through, and I choose that number. That's it. It just means that 95% of the population is smaller than the number, and 5% is bigger. So it turns out that you almost never have a sample at the 95th percent. You're between some sample, or you have statistical error in the collection of the data, so you don't actually know the exact values around that. So you have to do estimations in that sort of window. And there are 9 statistical methods for doing that. And they result in different answers. And again, do we have any statisticians in the crowd? Like actual, like graduate level statisticians? It's really interesting. So if you go in and you say, here's the quantile to a statistician, they will kind of look at you weird because they haven't heard the question yet, and the methodology for calculating the quantile would be dictated by the question. So if you're asking for the 95th percentile, that's one thing. But if you're asking for how many things are faster than 100 milliseconds, that's a different type of question. There's a different type of math that's used. Happens to not be tdigest. That's optimized for that. So if you use histogram data, you kind of get your typical histogram. I'm sure everybody's seen a histogram before. Basically, it's a density graph. The higher the bar, the more samples that were in that window of latency. So in a histogram view, you would have the number, the measurement, what's normally on the y-axis, on the x-axis. So on the bottom is like the latency. On the y-axis is the number of samples that were in that latency bin. So in this one, you can see at the median, we have a lot of samples. We have like more than 2 million samples. At the medium, around 500,000. And then the average is there, and you've got 90th and 99th percentile. This is a very unlikely distribution. You would probably never see something that looks just like this in production, even though I pulled this at production graph. So if you were to look at that over time, if you would take this histogram, and instead of drawing it this way, you kind of drew it this way towards you. So you would colorize instead of using long bends. So the higher bends, say, are like a rich red. Think of Doppler or radar. And the smaller bends are like green. In our tooling, I don't have a picture of our tooling because it's trying to not be vendory. But in our tooling, we actually use color density to do that. So we would keep it all green, and we use dark green when it's a hard bin, and we'd use very light, like a transparent green when it's a small bin. And then you can take those histograms and actually slot them over time. So now, in this case, we're looking at, I think they're about half an hour long. So each of these kind of bars is a half an hour of time that shows me a histogram. And the red spots are where I have a lot of samples, and then the black at the edges is where I have almost none. So I'm seeing the histogram kind of converted back into a time domain axis, which is pretty useful. Kind of the beauty of this thing is that when you have this, if you have data to populate a graph like this, you can actually calculate accurate percentiles over arbitrary periods of time, and they can be arbitrary percentiles. So you can ask, what's my 99th? And you can turn around and say, actually, what's my 99.2? What's my 75? What's my 50? What's my 25? Everybody likes mins and maxes. What's my 0 and my 100%? So if you have this rich data, you actually can do some really interesting things. So using that, you end up just effectively doing a count below, just like you would do in Prometheus, except that instead of like the 1 or 5 or 10 bins that you would have in Prometheus, you have kind of an arbitrarily rich set of bins to choose from. So you can go back and change your questions. Instead of asking how many are below 100 milliseconds, maybe it would better fit your system if instead of saying 99% are below 100, maybe it's really that I want to make sure that 99.99 are below 1,000. Right? Like maybe that's better. And we'll get into the maybe, which is kind of the whole problem with SLOs. So it's really important to remember that the questions we've asked all along are not percentile questions. And that's the big kind of got you with SLO management. All these tools are showing you the 99th percentile. And that's not what you really asked. You asked how many things were below 100 milliseconds. Right? You don't actually care so much how fast the 99th percentile is. You care what percentile is at 100 milliseconds. This is an inverse percentile or an inverse quantile. There's no such thing as an inverse percentile. So what does a real graph more or less look like? Now we have something that looks a lot richer and a lot more interesting. And if you have a really big service that actually is well behaved, this is data from a content distribution network. So this is over 1 second period of time, the latency for setting up the TCP connection from 2 different nodes. So we get about, maybe it's probably about 150 million. 150 million TCP connections came in, got set up in 1 second. And then we measured the latency and built this profile out. So it's really, really interesting to start looking into the data that way. So not only are these histograms super useful for calculating SLOs correctly and managing performance, but they're also really good tools to understand the behavior of your system. It gets really, really interesting that I have 2 modes here, because most systems don't behave that well. So if you do, for example, disk latency, you're going to probably have 4 modes. It's pretty interesting. Most people think that there's 2. There's usually about 4 modes for disk latency. If you have spinning disks, it can be 5, 6, 7 modes for disk latency. As you have, great example of this in kind of the histogram world is spinning disks. Does anybody still use spinning disks? Because I do, but I think most people are just like, I have left that behind. So in spinning disks, there's this amazing thing that in order to be fast, you put your data, if anybody remembers from computer systems architecture, you put your data near the center because the thing spins faster in the center, right? You get more data reads. Your latency is less in the center. If you want to do long sequential reads, you can put it out near the edge of the disk because at the same rotational rate, you cover more surface area. So people who build disk firmware think about this stuff all the time. That's why it's their job. What's really interesting is that you're putting stuff at the center of the disk that you need to be low latency. Guess what happens when those blocks fail on the disk? The firmware is really smart. It doesn't want to tell you your drive is bad, you should RMA it. It says, this block is bad, I can't write to it, we have errors on it. I need to give you a different block, but convince you it's the same block. So it'll remap. Right? So it'll remap a new block into that block. Where does it get the block from? The outside of the disk. So you're in your database and you're trying to do all this like really fast, low latency stuff near the center of the cylinders, right? And then suddenly you have bad blocks, they remap, and your latency goes through the roof because every time you hit that cylinder, that sector you think is in the center cylinder, the arm on the disk has to swing all the way out and then all the way back again. You can see it in 1 second pop up as a new mode on a histogram. Like it'll take 18 hours for Smart to be like, well, because what happens when you do this with a disk head for 18 hours straight, really hard after the thing's been in service for 2 years, right? The disk goes, but it takes a while. So the Smart status on the disk will tell you that it's broken about 18 hours after like the problem arises. But since then, you have all these horrible outliers in your database performance. This is the same true on caching servers and stuff like that. If you take all of the latencies, so for example, you're running Linux, you use eBPF, and you monitor the I/O latency of every single IOP against the drive, jam it into a histogram, which is really cheap. You can see inside 1 second that you have a new mode and your disk is screwed, and you can offline it. And it costs almost nothing. It's like 0.1% overhead on the box. So there's some really, really cool things that you can do with histograms. And in reality, histograms tend to look a lot more like this. This is 3 different histograms, but there's modes all over the place. So the interesting part, and I'm going to get into the histogram stuff, the histogram tech that we use, which is called libcircllhist. It's a log linear quantized histogram. It's BSD licensed. It's in C and Java and Go and JavaScript. You're more than welcome to it. What it does is it gives you a guarantee that basically a log linear quantized histogram means that it's logarithmic, base 10 in our case. So you can see from like 100 to 1,000 and 1,000 to 10,000 and 10,000 to 100,000. You can see at each exponent, but inside those exponents you have kind of a linear progression of data. So what we do, and you can kind of see it in the graph, from the 10 to the 15, there are exactly 5 bins there. We can show from 10 to 11, 11 to 12, 12 to 13. But if you go down below that, you can not only see from 1 to 2, you can see from 1 to 1.1, 1.1 to 1.2. So the way that works is basically you can describe any 2 digits, like 7.8 or 2.4 or 4.2, times 10 to the whatever. And that's sort of the granularity you give. The beauty of that is that every histogram in the system has the exact same bins. You're guaranteed incredibly low error margin inside the bins. So you have 4.7 error in the worst case and 0.5% maximal error in the best case, depending on which bin you're in. But the beauty is you can put them all together. So in the disk example, I'm tracking all these latencies across all my disks. I can have 10,000 disks in my data center. I can look at all of those histograms merged together, and I don't introduce any new statistical error into the questions that I ask. So you should use that. If you're using Envoy, for example, that's already under the hood. They already use the log linear quantized histograms. Sadly, Prometheus supports this, assuming you want to give it 43,000 bins as an answer set, which Prometheus goes and falls over. So you can't really use it with Prometheus, but it's under the hood there, so you can get it out. So, kind of talking about SLOs very specificcally. When we say, these are kind of the main takeaways, when we say 99.5% of requests should be faster than 100 millisecond, we're not actually caring as much about what the 99.5% is. We're caring about the 100 millisecond more as SREs. Like, that's really what our objective is. We've decided, I mean, like, kind of in a brutish way, if you care about the 99.5%, you've decided certain people, enough of them just don't matter, right? Whereas 100 millisecond, you're actually dictating an experience level, right? And it's a much better thing to decide what experience is acceptable as opposed to how many people you don't care about. So just a much better construct. So what you really care about is an inverse quantile. And this is sort of why T-digest is not the right approach, because T-digest, super, super cool and clever. Moment sketches, I think, are even more beautiful. They're about the first question, not about the second question. You can approximate, but you kind of get the wrong answer a little bit. And you can't, the most important part is you can't define how wrong it is. So like, you get the wrong answer, and you don't actually know how wrong it is. So framing SLOs correctly is important, right? So if you are actually doing SLIs and SLOs in your organization, like completely, you are actually directing your team to behave in certain ways, whether you hit those SLOs or not. If you're not hitting your SLOs, you're probably going to ramp back on innovation and ramp up on a reliability investment. That's a significant change for an organization, right? That's a directional change in an organization, right? So if reliability becomes a problem, you have to back down on how quickly. You can't move fast and break things anymore because you've clearly broken them too much, right? You have to slow down, and you have to invest in reliability. This has a lot of consequences for business, right? Time to market, innovation, all of this stuff. So it's really important that you're asking the right questions and you're doing the math right, because there's nothing more embarrassing to realize that you've invested all these resources and changed direction, and you were actually doing fine. So that's bad. And I've seen that a lot of times. When we go into organizations, they'll be measuring the wrong thing. And things will be really bad and they don't know it. Things will be great and they think that they're bad, and they're constantly kind of just incorrectly applying themselves. So in particular, two of my favorite, I'm kind of a math junkie, but two of my favorite things, moment sketches are really interesting. You end up storing like multiple higher order moments of a data set, and you can very accurately calculate arbitrary percentiles or quantiles in that range. But you're calculating the quantiles, not the inverse quantiles, and the way that it approximates and fuzzes the moments in there, or like the kernel density that you have, means that you don't have really good accuracy coming out, and as you start to merge them together, you introduce error that isn't bounded the right way. So you still have bounds, but the bounds start to grow, and you don't want that. They're typically used for other scientific things like estimating cardinality in database indexes, and stuff like that. They're really useful for doing that. If you're doing an online system where you're trying to report like slow query logs, like I want to log slow queries. Well, what's a slow query? Slower than 2 seconds. Okay, that's actually really a horrible definition of a slow query. Because like a query that normally takes 1 millisecond that takes 8 milliseconds is actually slow. So the techniques that you would use there, you could use histograms, but actually T-digests are probably better for that, is that you would, for a certain class of query, you would just track how fast they are, and if it's more than 99% of, if it's in the slowest 1 percentile, you log it out. So then you have like a dynamic sort of self-learning slow query log, and that's typically what that stuff is used for. So the most I would think the biggest takeaway, which is probably no one does this, and I think mainly because Google brought SLOs to us with a lot of marketing dollars and the O'Reilly book and everything like that, but they really didn't bring some of the nuances to it. People go in and say, we have SLOs, it's 99%, have to be faster than 100 milliseconds. Well, why? Why isn't it 99.2%? Why isn't it 115 milliseconds? And I will posture to you that if you can't answer that question, maybe your SLO is not such a serious thing, right? Those numbers should mean something. If you're going to be investing dollars around not hitting them, like, you should be able to justify why they are what they are. And most people cannot do that. They're chosen arbitrarily, right? Now, I think measuring things is really useful. It can tell you changes in behavior of the system, you can identify regressions, you can do all sorts of stuff. But when you start to build budgets, whether they're financial or not, even time investment budgets around these numbers, now you're taking them to a level where you actually have to have confidence that they're right. And the best way to do this is to establish an arbitrary one, perhaps not tie budgeting to it, but iterate. You have to fit those numbers into something that's a real goal established by the business, right? Is it user attrition or user churn? Is it purchased products? Is it shopping cart checkouts? Is it delivery schedule times? Is it new signups? I mean, if you're just Instagram, it's the number of views, right? Whatever it is, your business has an optimization case. You need to parameter fit these numbers back into those numbers. And if you don't store your data over long periods of time, you can't go do that again, right? So if I just track 100 milliseconds with Prometheus as a bin boundary, I can't go explore the parameter space and try to better fit my SLO to what actually matters. So keep the data around. I highly suggest keeping them in histograms. And then iteratively optimize the parameters. So go back and try to understand, and you can do this, we do this programmatically, but I think that it's pretty easy. It's sort of only 2 variables. We'll get to why this is a little bit harder in the next slide, I think. But you can just kind of dial those up and down and try to fit it into the other business indicator, right? You have some sort of graph that shows business health or a business objective, and you have to fit to that. So the undiscussed problem that's often here is that like the first slide said 99% are faster than 100 milliseconds over 28 days. That's a horrible, horrible thing because you don't really want to measure your 99th percentile over the whole 28 days. Ideally, there are 2 time periods that you have to consider. One of them is whether or not you're fast enough now. And what is now? Now, maybe it's 5 minutes. So in an example, you say 99.5% are under 100 milliseconds over any 5-minute period. So I look at every 5-minute period throughout the month. I do an accurate quantile calculation. I figure out how many are too slow. And then over that period, over the 28 days, I figure out how many of those 5-minute windows I violated and how many I didn't. This is a much healthier approach. I don't know if anybody sees a glaring problem with this. There's one glaring problem with this, is that, and this is sort of the problem that most people have when they use tools like StatsD and things like that to collect the quantiles, is that this isn't normalized for user arrival rates. Right? So like, I actually don't care if I, screw up the 5-minute window, screwing up the 5-minute windows at 3 a.m. when no one's on the site. Right? I actually really care a lot when it's a holiday and everyone's using it, or it's 3 p.m. in the afternoon and everyone's, trying to book their dinner reservations on my reservation site. It's really important that it's up then. So you do need to really think about the business aspect when you're designing your SLO so that it actually fits against business objectives. The problem is we just went from 2 parameters to now 4, right? So we need to know over what time period we're measuring our kind of quantile latency. So we have 99.5% or under 100 milliseconds over 5 period. So that's 3. And then we need to know how many of those periods over what sliding window. So that's actually 2 more. So there's actually 5 parameters. The last parameter is really easy to just get right. So it either needs to be a month or it needs to be a quarter, because that's how people get paid, right? So you get paid, your bonuses are calculated, probably at the end of the quarter, even if you don't get them at the end of the year. And you also want to be able to win. Teams need to win. You need to be able to set objectives, and the teams need to be able to hit the objectives so that they feel good, right? Which is why these numbers should never be 100%. You're guaranteed that everyone's going to fail. So setting that to 28 days and fixing that parameter is a pretty good bet. Tool choices. So you should just use our product. But I think there are 3 really important aspects to get these things right. And you can do this very easily with like Splunk and Elk and Elastic and things like that. And then you can also do it with tools that are really designed to kind of answer SLO-oriented questions. One thing is you need correct math, right? So you either need to use a tool that uses raw data or binned histograms. And the easiest way to trust that is that if the tool doesn't tell you how much error is in the answer, then you shouldn't trust it. That's the easy one. So when you get your 99th percentile, so this is actually a really common thing. How many people graph percentiles with Prometheus? Yeah. The count under is precisely accurate. The percentile can have like 1,000% error easily. 1,000% error. It could be 10 times wrong, right? Because the bins can be so wide in that. Like if you have a bin from 16 to 32, like and people tend to have really wide bins. They'll have a bin from 1,000 to 2,500. And you have some data points in there. It has to approximate the 99th percentile. It just gives you some number that's like probably, I don't know how Prometheus does it, probably does a linear interpolation and goes through that like super large bin. No idea what the answer is. And they're not very honest about it, because when you ask the question, they don't say 38.7 with an error margin of 1,000%. They just give you a number, and it's like, oh, that's my 99th percentile, and it gives you a confidence that should not be there. So you definitely want a tool that does the math correctly, especially if you're going to be building budgets around it. So the other thing is you need history. So you need to keep your data because your numbers are made up and you need to improve them. And the only way to do that is to go rerun your analysis on the old data. And the last thing you need is correlation. So the tool, like I said, you have these parameters, you need to fit them. You have to fit them to some other signal. If you don't have the signal in the system, it becomes a lot harder. Basically, it becomes like a crazy Excel exercise, where you have to pull some signal into Excel and you pull all of your SLO data into Excel and you try to do some sort of parameterization fit, which is a pain in the butt. So you really want the system that has your latency data in it to also have the business signals you're trying to fit to in it. So that way you can use the same tooling and the same data science tools to try to fit these systems together. So those are the 3 things you're looking for. I think there are a lot of products that fit this. I obviously love mine the best, but there are a lot of ways to do this. But this is what you should be looking for. And that's it. Does anybody have any questions? Someone. Oh.
You touched on it briefly with your database example, but can you talk a little bit about trying to measure latency for actions which vary wildly in size? Like, in CDN serving, you have wide distributions of object sizes. Database queries can be wildly different in how expensive they are, but you're still trying to compare the latency of these dissimilar things in some.
Yeah. So the question is if you're going to be setting, I think I'll sort of translate that into a slightly different question. But if you're going to be trying to set latency objectives around things, and those things have widely varying latencies, how do you set something reasonable, right? If my database query latency needs to be less than 1 second, is that even fair? Because I have weird queries that run in the system all the time, and I should have different expectations for different queries. And I think that's what it comes down to, is that you really need to have very well-established expectations for a class of things you expect to behave a certain way, which is why loading a home page probably should be the same experience for every user, right? But fetching a block out of Ceph, or a file out of Ceph, or something out of S3, or performing a restore, like those things can have widely varying times. Generic databases, like an SQL database, you could run a query that takes 15 minutes that's very OLAP style, and you have other queries where you would be destroyed if they took more than 1 millisecond, right? They're selecting a single row or single column and a single row. So you really need to basically cluster them based on expectation. There are techniques to auto-cluster those things. Those are pretty hard. Most products out there don't do that internally. I gave a talk 2 days ago about all products should do that internally. It's a hard problem, but what you end up doing is you end up doing basically, you store a certain amount of data fairly richly with dimensionality, and then you do like k-means clustering around that data, so you identify groups of data that should behave certain ways. And then you have to, which is the hard part, that's the easy part. The hard part is that you have to go and look in those and find characteristics of them that you think classify them, right? You have to basically fingerprint them so that when you get a new query, you say, oh, I don't know how fast you are yet because you haven't finished, but you should fit into this cluster. And then you can measure it against those and do like dynamic slow query logging and stuff like that. I think it's way out of the realm of SLOs, but I would say that setting an SLO around like arbitrary database queries would be really hard. Setting an SLO around disk I/O latency would not, because at the base layer, everybody's just asking for a disk block, right? So if you have a specific workload on that, it should be really self-consistent on the server. It works.
I have two different questions. First one is about sampling. For example, I have a very big application, and the app writes a shit ton of logs. I cannot store them all because it's very expensive, and I will spend my entire budget for just writing and storing logs instead of serving users. Simple answer is to sample these logs and flush on the disk just 1 of 10 or 1 of 100. The question is, in what circumstances I can rely on my sampling and how I can prove to myself that, yes, my sampling is okay, and I can keep 1 out of 10
right,
and use it for SLO, latency SLO calculation. And the second question is, for example, it's a bit far, but it's more related to distributions. I have 100 servers. I know I want to check how hot they are from CPU load point of view during the peak load. Basically, if I will try to calculate average or mean value, I will be blind. It tells me nothing. What if I apply the same percentiles? How precise I will be that, yes, okay, my 99th percentile, I don't know, 70% load around my 100 servers. I'm safe, I can survive during the peak load, and I can put even more traffic into specific.
right.
I don't need more servers to survive with 1K more requests.
Okay, so your first question is about logging. I have a very controversial point of view on that, is that you shouldn't be logging anything. I mean, especially with GDPR, like the best way to be happy with privacy concerns is if you don't write any logs, you don't have to delete anything. Histograms are really, really cheap. So the histogram implementation that we have that's open source has a flat 9 nanosecond recordation time. So if you're measuring anything that's significantly larger than, say, 3 times that, so like 30, 40 nanoseconds, like it's just nominal overhead to use a histogram to log that. Logs have a lot of other value to them, and I would say that using them for the math for SLO calculations is probably not a good idea, but using them and doing sample to figure out which logs are important logs, if you can't afford to store all of them, you log 100% of errors and you log some small sampling like 0.1% of non-errors. And then that way you have a representative sample of logs, but you actually track every latency in a histogram. So then you have the right answer. So you should be able to sample at 100% into a histogram without any cost, like any real cost. The second question was about how do you identify servers, like hot CPU servers, during high load times. The typical way to do that, I mean, you can sort of use histograms to do that, but typically you just take CPU measurements off of all the servers and store them as separate signals. And then you can do some trivial outlier detection algorithms. So a lot of this is sort of like ask a statistician. So latency profiles tend to resemble gamma distributions. Arrival rates resemble Poisson distributions. And then you have, if you're like delivering, so CPU is a saturation question. So you should be able to model that probably pretty successfully with something like a reversed gamma distribution or even a Gaussian distribution if you're not hitting 100%. Right? So if you are not pegging the CPU, you should have a relatively normal distribution around some number, whatever that number is. So at peak time, I know the CPU utilization on my 100 machines. I can put them all into the system, create a standard deviation around that, right? And then I could say if it's 3 sigma above the standard deviation and 6 sigma below the deviation, then I have a problem, right? It's an outlier. So you can do that with histograms, but it's a little overkill. I think you could just use like statistical outlier detection. So that's a common process in machine learning where you have a whole bunch of samples and you don't want to train on the bad ones, so you kind of throw away the bad data. The techniques used identify to throw away the bad data are the exact same techniques you realize that server's bad data. Like I should probably pay attention.
So I've heard you say a few times over the last few days that logging is not something you think we should be doing. How far do you take that statement?
How far do we take that statement?
Like, are you talking about let's not even log, traffic logs from the load balancer? Do you think those things shouldn't be logged either, or?
So, correct. I do think. We run in GCP. So if I don't, apparently it's a racket system, right? I just want to know. I want a histogram of like every response code by endpoint out of the load balancer. They can't give me that. The only thing they can give me is logs. So I have to put the logs somewhere, and then I have to run them through like Bigtable to get my answer. It's like super annoying. But then we delete them after that. Like we just put them in, get our answers out, and throw them away. Application logs, we don't really write logs. There's really no logs. I mean, our systems probably accidentally write like a couple kilobytes of logs a day. If we have an error message, we use error reporting services. Like we use Backtrace, but like Sentry and those other ones. So if you have sort of an anomaly in the application where the vast majority of logs that I've seen in my life that are useful are application developers saying, this just went wrong. And I would argue that's probably not the place you want it as in a log. You want it in a database that categorizes things that have gone wrong. And there are services that do that. So I don't write much logs.
So I guess my next follow-up question is then how do you do forensic analysis in the cases of security breaches or things that have gone really wrong, or even an accidental one where you've accidentally purged your entire database due to a shitty query or something like that?
So for compliance reasons, you sometimes have to write logs, and that's sometimes the case. It's kind of one of the beauties of microservices. I think microservices are a horrible problem of distributed systems we brought on ourselves, but each component can define its compliance requirements, its risk, and then define that policy for itself, which really limits the scope of what you would need to write logs for. So if you have payment services or customer PII or something like that, you can isolate it in a way where you have audit logging inside of that microservice. That's super important. But then outside of it, in your caching layer, you just don't write logs. And then in most systems that we work in, there's some sort of tapped packet capture device that security team can do whatever they want, right? So, but from an application perspective, if I'm writing a Java app or a Node app or something like that, or Go, tend to not write logs. Like I said, it is controversial opinion. A lot of people disagree with that. I'm okay being right. All right. Well, thank you very much.